Hi, welcome to an audio test session with APX. These videos provide worthwhile information for APX users and demonstrations on a range of audio measurement applications. In this session, Mike will discuss and demonstrate loudspeaker test methodologies.
Greetings folks, Mike Martin here with Audio Precision. Welcome to this edition of Audio Test Sessions with APX. In this session, we will be discussing typical loudspeaker test methodology, typical equipment configurations, and the software solutions that Audio Precision has produced to address this testing need. But before we jump into the details, let's take a quick look at the system in action. Here we will run the loudspeaker production test measurement set. Within 7 seconds of starting the test, you have a complete set of the most important measurement results for evaluating a speaker, including frequency response, THD, rub and buzz, impulse response, impedance, and teal small values, all without moving a single cable. This plot shows the measured frequency response for a very good speaker. Achieving this level of result is not just dependent on the DUT. It takes attention to detail to get the optimum results for a given environment. Next, we'll do a quick review of some of the methods used to perform electroacoustic test. Acoustic reflections are the nemesis of acoustic measurements. Perfectly anechoic measurements are not possible, but there are techniques that can dramatically improve your results, even in difficult conditions. The next 6 slides briefly cover each of the options shown here to help mitigate the reflections. Acoustic testing outdoors, technically called free field testing, can be done with excellent results. A wide open field, well away from reflecting surfaces, is ideal. The downside is that weather may limit when you can do your testing, and uncontrollable external noise sources such as wind, sirens, or jet planes may force retests. This photo shows 2 techniques being used simultaneously. Free field testing has been combined with the ground plane technique that we'll discuss shortly. Anechoic chambers provide very low reflection environments, but building a chamber is very expensive, and lower frequency coverage requires a very large chamber. The typical setup has a speaker and measurement mic mounted on tripods with a distance of 1 or 2 meters between them. This is the conventional elevated far field measurement. Ground plane measurements are interesting as intentional reflections are produced, but these reflections are constructive and result in a 6 dB increase in sound pressure level at the mic for a given test distance compared to a standard elevated far field measurement. The measurement mic is placed flat on the surface at a distance that is at least 3 times or more the longest dimension of the DUT. This technique is a practical way to achieve good test results in a lab or office environment. Windowing uses DSP capability built into the test system to digitally shorten the measured time response to cut out some reflections. Shown in the upper left is an example of typical floor bounce. The timing of this bounce is very deterministic and, using the formula shown, can be calculated quite accurately. However, this technique is a bit problematic if the reflection time is short. Shortening the measurement window directly reduces the resolution on lower frequency response. In this case, you might be forced to make near-field measurements to acquire an accurate low-frequency response, and then merge the data sets together to produce a more accurate overall response plot. Audio Precision APX measurement software includes windowing, and one of the nice features is that you can move the window on the impulse response plot or the energy time curve and watch how this change affects the frequency response plot. You can easily see how big of an impact the windowing changes make on the measurement. For near field testing, the microphone is placed as close to the center of the diaphragm as possible, while allowing clearance for the full movement of the diaphragm during the test. At low frequencies, the driver acts as a rigid piston. In this configuration, the reflections and noise are eliminated from the measurement, producing an accurate representation of the low frequency response. However, this technique is only valid up to a few hundred hertz. So, to get a full picture of the speaker's frequency response, it is necessary to splice the near field response with the upper portion of a far field response. It is not unusual to combine some of these techniques to get the best results possible for a given situation. Here we see the basic functional blocks of the loudspeaker test system. Ideally, the flatness of the frequency response and the distortion of these items is significantly better than the device under test, so that the variations seen in the data are due primarily to the DUT. This is typically true of instrumentation-grade equipment. The sense resistor shown on the return leg of the amplifier is used to determine impedance of the loudspeaker. This is usually a very small precision resistance, typically in the hundreds of milliohm range. And of course, adding a computer allows for automation, as long as the instrumentation supports it. For the purposes of this video, I am using what might be considered an R&D setup, with an APX 525 audio analyzer and an APX 1701 transducer interface as shown here. The equipment provides all of the functions needed to perform loudspeaker testing. The APX 1701 is a two-channel device providing support for use of two measurement microphones and dual amplifiers, allowing for either single speaker or dual speaker measurements. This can be handy for production tests, where it's often desirable to be setting up the next device while the current device is being tested. As previously discussed, a near-field measurement can produce very good low-frequency results. The system shown here is configured to make both a near-field and a far-field measurement as parts of a single sequence. Note that I have shown an APX 526 analyzer here, which has 4 inputs, providing coverage for the 2 mic inputs and the sense resistor input. Shown here is an alternative solution called APX 500 Flex, which is targeted at providing low-cost test solutions for production tests through the use of third-party ASIO audio interfaces and other accessory items, rather than the traditional APX 5XX series hardware analyzers. This platform uses the exact same APX 500 measurement software that is used with the AP hardware analyzers and will produce results quite similar to those shown in the following measurements. One comment here: we know the frequency response of the measurement mic, which is stated by the manufacturer and/or contained in the TEDS data, but we don't know the flatness of the third-party power amp. It is therefore necessary to characterize the frequency response of the amp and create an equalization curve that calibrates out the amplitude variations based on frequency. Next, we will do a quick overview of the APX 500 measurement software user interface, then move on to perform setup and running of an acoustic response test of a driver, a loudspeaker production test of a driver, and as a bonus, a setup and test of a Bluetooth speaker. The APX 500 measurement software can be run in 2 modes, sequence mode and bench mode. We will be using sequence mode for the following demonstrations. The sequence mode UI is comprised of 4 main panels. From left to right is the navigator pane, the signal path setup pane, the results display, and in the lower left corner a set of monitors and meters. The navigator pane controls which tests will be performed and in which order. The signal path setup pane defines the connections to be made for a specific signal path and the instrument settings. The same pane can also be toggled to show and control individual test-related settings. The results display on the right side of the screen shows all of the measurements made, which may be meter-type measurements, may be plots, or a combination. The lower portion of this area shows a thumbnail view of each specific result available from the running of a single test. For this test, I've configured a ground plane test on a table in a semi-anechoic chamber. In this case, the floor is reflective. To set up a new test, start with the standard APX 500 project. Click on the Add Measurement button and select the Acoustic Response Test. Click on the Add and Close button at the bottom of the Add Measurement window. In the Navigator pane, scroll down to the Acoustic Response step in the sequence and click on the checkbox to the left of that test. If we scroll down to the bottom of the sequence, there is an item called Report, which we will unselect just so that it isn't popping up each time we run the test. Next, we will set up the signal path. By clicking on the left arrow, we will shift the view in this pane from the test setup to the signal path setup. We will start the signal path setup with the output configuration. Since we are using the APX 1701, we need to set the output connector to transducer interface. We are only testing a single driver for this test, so we will set the channels control to 1. We will be using amplifier input 1, so click on amplifier 1 to turn it on. Leave the acoustic box unchecked. Scrolling down to the input configuration section, we need to first change the connector to transducer interface. We have only one input, the microphone, so we set channels to 1. Again, leave the acoustic box unchecked. The values for the next 3 items in the list can be left to the defaults. Since we are using an unbalanced measurement mic, we need to turn on the constant current power supply. We are going to be using dB SPL units, so set the unit at the top of the results graph for RMS level to dB SPL1. Next, we download the TEDS data from the mic. Click on Set dB SPL, then click on Calibrate from TEDS button in the pop-up window. This opens a secondary pop-up window. Click on the Read TEDS button. Once the TEDS data is displayed, click on the Set Sensitivity button, then click on Close, followed by closing the MicCal window. We will now set up an output reference. Setting a value here propagates to other controls that need an output level setting. Make a mental note that the dB/RG box is initially set to 100 mV RMS. Under the Analog tab, scroll down to the Auto Gen Level button and click on it. When the pop-up window appears, set the Regulate pull-down to RMS level. Using the Target Value pull-down, select dB SPL1, which automatically enters 120.775 value into the box. Then edit that value to 94 dB. Next, we will set the range that the analyzer uses as the bounds for the automatic level search that will find the 94 dB SPL level. The first time you do this, you may find yourself having to empirically arrive at good values. In this case, I've determined that a 1 volt start and a 3 volt stop setting does an efficient adjustment. Also, it seems that an initial steps setting of 3 sometimes works a bit better. Once these settings have been made, click on the Start button. This begins the automatic output level adjustment. You can see that the system arrives quickly at the 94 dB SPL setting, which is displayed on the right side of the screen as the measured level. Note that the dB/RG box in the reference section now shows 1.429 volts RMS, which is the output voltage necessary to achieve a 94 dB SPL for this particular setup. Note also that the Verify Connections level has been automatically set to that same value. This completes the signal path setup. Next, we have a couple of settings to make in the acoustic response test settings. Click again on the left arrow at the top of the signal path setup pane and go back to the measurement settings. Here we need to set the level that will be used for the sweep to 0 dB/RG. This specifies that the sweep will be done at the RG level, which we have set to 94 dB. At this point, we have made the necessary settings and we are ready to run the sequence. Click on the blue Run Sequence button in the Navigator pane to start the test. Once the test completes, the measurement data will be shown in the Results section on the right side of the display. Note that each result can be selected below the graph, showing the data for each measurement made. You may find some of the data displayed is off the graph. This can be addressed by simply auto-scaling the data. To do this, hover the mouse pointer just above the end of the y-axis title, which causes a small down arrow to appear. Click on this and then scroll over and click on Auto Scale. Note that the single sweep produced all the measurements shown. Frequency response, THD, rub and buzz, and other measurements were all measured simultaneously. If you prefer to have the level adjusted at the beginning of each run, click the Measurement Sequence Settings item just below the signal path setup line in the Navigator pane. This opens a pop-up window. Click on the Auto Set Generator level under the References column. Once you have completed this setup, save it as a project or template file under the menu item File using Save Project As, and assign the file a meaningful name. The next time you need to run this test, simply open that project or template file and all of the setup will be done automatically. I talked about floor bounce earlier in this video. I've reconfigured the test setup to be a standard far field configuration with the same driver and the same measurement mic that we have been using, but now configured for elevated far field testing, separated by 2 meters in the same semi-anechoic chamber used for the previous measurements. I also used the same acoustic response project that we just set up. A quick click on the Run Sequence button produced a set of new results. In the impulse response plot, you can see a ringing in the response a couple of milliseconds after the impulse. This is the acoustic signal bouncing off the chamber floor and arriving at the mic a bit later than the initial impulse. Looking at the frequency response, we see that the response now has significantly more aberrations compared to what we have seen with this same DUT previously. As a first step, we will adjust the windowing to cut out this reflection using the impulse response view. After making this change, the frequency response plot above 1 kHz looks a bit more normal, but we see that the lower frequency range is quite different. Note that the energy time curve provides better resolution to the reflection edges than is shown in the impulse response plot. This view shows just how close to the initial impulse the reflection really is. We cannot expect to get a good representation of the low frequency range with this configuration. This particular setup in this chamber is not the best choice, which is why I've been using the ground plane technique in the chamber up to now. Next, let's go back to the ground plane configuration, but this time test using loudspeaker production test measurement set. This setup is quite similar to the setup for acoustic response, so I will focus only on the differences in the setup compared to acoustic response. In the navigator pane, you can see that I've added a second signal path. This allows me to keep the acoustic response test unchanged in the same sequence. After adding the new signal path, I added loudspeaker production test measurement using the Add Measurement button. Now we need to set up this new signal path. With the loudspeaker production test measurement highlighted, go to the signal path setup pane and click on the left arrow to get to the signal path setup. The output settings are the same as acoustic response. There are a couple of changes in the input configuration. We are still using the transducer interface, so that is still selected. However, now we have 2 input channels. One is the measurement mic and the other is the current sense signal to measure the speaker impedance. Set channels to 2. From here, we toggle the left arrow in the signal path setup pane to get to the measurement settings. We need to scroll down to the analyzer settings. The test configuration should be set to external 1 channel, and the channel sense should be set to channel 2. The test setup is now complete and the test can be run by clicking on the Run Sequence button. However, we saw this in action in the beginning of the video, so I won't repeat it here. Next, we'll set up to test a Bluetooth speaker. Starting with the standard APX 500 project, we need to add 2 measurements. One is DUT delay and the other is the acoustic response. Once that is done, move to the signal path setup. This time, we will not be selecting transducer interface for the output connector. Instead, we will select Bluetooth. Turn on your Bluetooth device and place into pairing mode. Select Bluetooth in the connector pull-down and then click on Scan. This starts the scan for your device. Once complete, the scan table will contain any devices found. Click on your device and then click on Pair. In the pop-up window, click on Pair Device button. Once complete, close the scan window. Next, click on the Connect button and select your device. A short pull-down menu appears. In this case, I will be using the A2DP profile. The Bluetooth setup is now complete. From here, we move down to the Input Configuration section. Since we are still using the measurement mic, we will use the transducer interface for the input connector. Set channels to 1. Turn on the constant current power supply. Next, set dB/SPL and go through the same procedure that you used with the previous acoustic response setup. In the pop-up window, set units to dB/SPL1. Click on Calibrate from TEDS. In the new pop-up window, click on Read TEDS. Once the sensitivity data shows, click on the checkbox for Set dB/SPL1, then click on the Set Sensitivity, and then click on Close. Finally, click on the Microphone Calibration Close button. Moving down to the Reference section, select the Digital tab. Click on Auto Gen Level. Once the new window opens, set Regulate to RMS level and target value to 94 dB/SPL. The start value of -60 dBFS and the stop value of 0 dBFS are OK. Set initial steps to 3, then click on Start. The system will now auto-set to 94 dB/SPL. You can see that in the reference level and verified connections levels have now been automatically set to -14.766 dBFS. Moving back to the Navigator pane, make sure that the DUT delay and acoustic response checkboxes have been checked. At this point, we have completed the configuration and can now run the test. Click on the blue Run Sequence button. Note that the DUT delay measurement shows 167 milliseconds, but the acoustic response data is nonsense. This is because of that 167 millisecond DUT delay. We must go into the acoustic response test settings and change the DUT delay to 170 milliseconds. Note that the delay can move around a bit, so it might take an adjustment or two to find a reliable value. However, as soon as we make this change, the next run of the test produces a quite good data set. The frequency response is quite flat over the range of about 200 Hz to 9 kHz. With that, we've come to the end of our testing. Thanks for watching this edition of Audio Test Sessions with APX.
Thank you for joining us for this audio test session with APX. For additional videos, visit ap.com or any of our social media channels.